we're now going to have a look at one of the reactions that haloalkanes undergo, and this reaction is the hydrolysis reaction. So firstly, just to break up what hydrolysis actually means, if we just break up the word, we've got hydro and we've got lysis. Now hydro means water, okay, so anything to do with hydro is water, and lysis means to break something apart. So essentially what we're going to do is we're going to break haloalkanes apart using water. We can either use water or we can use an aqueous solution of hydroxide ions, because even when we do that, we're still technically adding a water molecule. So let's have a look at firstly how these haloalkanes react and why. So when we're looking at haloalkanes, they all have this bond present, which is the carbon halogen bond. So again, this X could be fluorine, chlorine, bromine, or iodine. Okay, and hopefully you remember that our halogens are very electronegative. So electronegativity is the attraction of the bonded atom to the pair of electrons in this covalent bond. So all of these halogens, so fluorine being the most electronegative, iodine being the least, but overall they are all more electronegative than the carbon. So that means in this bond over here, the shared pair of electrons are always going to be lying closer towards the halogen than they are towards the carbon. And that means this bond here will always be a polar bond. So we have a delta positive on the carbon and a delta negative on the halogen. So we have this polar bond. And it is because of this polar bond, these haloalkanes are so reactive. Okay. This carbon delta positive, which is going to be common in all of our haloalkanes, these attract something called nucleophiles. So we've looked at electrophiles. Let's now have a look at a nucleophile. Okay, so a nucleophile, the correct definition of this is that it is an electron pair donor. Okay, so that means it wants to give a pair of electrons. Okay, the nuclear part, the phile part, together just means that these are attracted to nuclei, so something that is positive. Okay, these are attracted to something that are positive because they have an electron pair to donate. Okay, so that means nucleophiles, a good way of identifying them is that they usually have a lone pair of electrons. So examples of nucleophiles that we may look at are water. So we know that water has not just one, but it has two lone pairs of electrons on the oxygen. We've got our hydroxide ion, which has a lone pair of electrons, or more than one lone pair of electrons on the oxygen. And we also have ammonia. So if you remember, ammonia on the nitrogen also has a lone pair of electrons. So all of these can act as nucleophiles because they have a pair of electrons to donate. And as they have a pair of electrons to donate, they are attracted to something that is usually delta positive, and that's what the carbon here is. So let's start having a look at the reaction and the mechanism for the reactions of haloalkanes. So first things first, in our spec, we're only expected to know the hydrolysis reaction of primary haloalkanes. So let's just quickly have a look at what we mean by a primary haloalkane. So primary haloalkane is where the carbon to which the halogen is attached to, so in this case this one, the carbon to which the halogen is attached to is only bonded to one other carbon. So this bromoethane molecule is an example of a primary haloalkane. Okay, so we're not expected to know the reactions of secondary and tertiary haloalkanes, just primary haloalkanes. So let's now have a look at what's going to happen in this mechanism. So let's imagine that we use an aqueous solution of hydroxide ions. So that means we're going to use something like sodium hydroxide, potassium hydroxide, and so on. Okay. And let's say we have our bromoethane available. So because we're using sodium, let's say we're using sodium hydroxide. Okay, sodium hydroxide is an ionic compound. In solution, that's going to form Na plus and OH minus. Okay, so in solution, we have these ions present. This Na plus is just acting as a spectator ion. It's not going to take part in the reaction, but this hydroxide ion will. So when it comes to drawing the mechanism, we only need to care about the hydroxide ion. So that means we should draw a hydroxide ion. We tend to put the negative charge at the end, but technically that negative charge is on the oxygen because the oxygen has a lone pair of electrons. So always draw the lone pair of electrons on the oxygen. So this hydroxide ion is our nucleophile. Okay, it's going to be attracted to something that is electron deficient or has a delta positive charge. So what we now need to do, like we always do, is draw in any dipoles. So as we said, the carbon-halogen bond is going to be a polar bond, which means it has a dipole going across that. And as usual, we need to draw curly arrows to show what happens. So our carbon delta positive, our electron deficient carbon, is going to attract this nucleophile. Okay, it's going to attract the lone pair of electrons here. So we are going to show the formation of a bond between this oxygen and that carbon. And the way that we do that is drawing a curly arrow going from the lone pair of electrons on the oxygen straight to the carbon delta positive. Okay. And what that will do is it's going to form a bond between the oxygen and the carbon. But that's going to mean that carbon has too many bonds, because remember carbon can only have a maximum of 4 bonds. So that means this bond here, the carbon-halogen bond, or the carbon-bromine bond, this is going to break. Okay, the electrons are already going close towards the bromine's ready to leave. So we need to draw a curly arrow from the bond, so draw it from the centre of the bond, going to the Br delta minus, like so. So let's now draw the product of what's happened here. So what we've done is we have formed a bond between the carbon and the oxygen. Okay, make sure your bond is showing the bond between carbon and oxygen, not carbon to this hydrogen. Everything else is the same on this molecule. And in that process, we have kicked out a Br. And because the Br ran away with the electrons in this bond, it now has an extra electron, so it has a negative charge and technically a lone pair as well. Okay, so hopefully you can see that when we do the hydrolysis reaction of a haloalkane, we form the corresponding alcohol. So this one we had bromoethane, and from this we have formed ethanol. Okay, not forgetting about the bromide that we've kicked out. So if I now do the overall reaction, so if I were to write, this was just the mechanism, if I write out the overall reaction, we had CH3, CH2Br, so this is our bromoethane. I reacted that with sodium hydroxide, and that has formed ethanol, which is CH3, CH2OH. And this bromide ion, remember what I said, the sodium ion is a spectator ion, so that is just going to go with that. Okay, and this is the balanced overall equation of what has occurred. So if we look at how we name this mechanism, so the name of the reaction is just hydrolysis, but the actual mechanism, the step-by-step of what happens, because it uses a nucleophile, this is going to be nucleophilic. And because we started off with 2 reactants and ended up with 2 products, and hopefully you can see that the OH minus comes in and substitutes the Br, this is called a nucleophilic substitution reaction. Okay, so this here is the name of the mechanism of the reaction. Right, let's just have a look at one more example. And I'm going to do this in the skeletal form so we can see how that is done. Let's go for this. So over here I've got 1, 2, 3, 4. I've got 1 chlorobutane. Okay, so 1 chlorobutane here. And again, imagine that I react this with, let's just say potassium hydroxide. Okay, if I react this with potassium hydroxide, I've got hydroxide ions present. Draw the lone pair on the oxygen. This is my nucleophile. On my haloalkane, my 1 chlorobutane, I need to draw a dipole. This carbon here is delta positive, and this chlorine is delta negative. My lone pair of electrons, I'll do this different colour. My lone pair of electrons is going to go over here. So we're going to form a bond with that carbon. So it's going from the lone pair on the nucleophile to the carbon that is delta positive. And then this carbon-chlorine bond must break, like so. Okay, just a reminder, if we're breaking a bond like this is called heterolytic fission, because both the electrons in this bond are going to go to, the chlorine is going to go to one atom. So if I now draw the product of what I've just done, so 1, 2, 3, 4. So I had 4 carbons here, 1, 2, 3, 4. I must have 4 carbons here as well. So I've formed butan 1-ol. Still got my 4 carbons. And I've also released a chloride ion. So that there is the correct mechanism. I've done my dipoles, I've drawn my lone pair in, I've done my curly arrows, and I've drawn both the products that have formed from my mechanism. This is still a nucleophilic substitution. If I were to do the overall reaction, or to write the overall reaction, that is going to be, I'm just going to do it structural. So this one here is 1 chlorobutane. React that, I said, with potassium hydroxide, and then I have formed the corresponding alcohol, like so. So I've now formed butan 1-ol, and I have formed KCl as well.